In this video, we will explain equilibrium of a body for grade 9. We will discuss three concepts: interaction of forces, equilibrium of a body, and Hooke's law. We will start with principle of interaction that we call it Newton's third law also. If we have two objects, A and body B, here we have the body A is the Earth and the body B is the Moon. When body A exerts a force Fa on B, the Earth will exert a force on the Moon, which is a force of attraction. The Earth attracts the Moon towards it. And we call this force A on B, means that the Earth is doing the force. A is doing the force. On B, B is receiving the force. So we will draw the force on B since B is the body receiving the force. At the same instant, B will apply another force. Force B on Earth means that B is doing the force and A will receive the force. So whenever body A apply a force A on B on body B, simultaneously at the same instant, the body B will exert a force B on A on body A. Thus, force A on B and force B on A are called action and reaction. Here, the Earth is applying the force on the Moon. This is the action. At the same instant, the Moon will apply a reaction on the Earth, which is force B on A. This action and reaction have same magnitude, have same line of action, but having opposite direction. Keep in your mind, the action and reaction will never act on the same body. Thus, the relation for the two interaction forces is Fa on B as vector equal minus Fb on A as vector. And the minus sign represents that these two forces have different directions. So for every action, there is always an equal and opposite reaction. Here we have the Earth and the Moon. We all know that the Earth attracts the Moon by a force, and this is the force, the blue arrow. At the same instant, also the Moon will attract the Earth with a reaction force Moon on Earth, which is applied on the center of Earth. Of course, as the Moon rotates around the Earth, always the two forces have the same line of action, equal magnitude, but opposite directions. Let us consider this example, a book on a table. Of course, the book will apply a force on the table, which we call it force book on the table. And this we will call it the action. At the same instant, the table will apply a reaction on the book, which is equal in magnitude, same line of action, but opposite in direction. And we will call it force table on the book. Keep in your mind that the force book on the table is applied on the table, the point of contact between the table and the book, but it is on the table. While the force table on the book, it is the same contact point between the table and the book, but the force is on the book, not on the table. By the way, this force, we call it the normal reaction. The force table on the book is the normal reaction, which has the symbol and vector. Let us consider another force on the book. The force Earth on the book. This is the action, and we all know that this force, we call it weight. Weight equal to mass times gravity. This is the action. Where is the reaction? Let us resize our picture. Here the book and the weight of the book, which is the force of Earth on the book, and the reaction should be force book on the Earth. So here the Earth, and here the reaction of the force book on Earth. It is applied on the center of the Earth, which also has the same line of action, same magnitude, but opposite directions. So we can recognize two types of interactions. The first, interaction from a distance, as the example we already did, the book with the Earth. And the second one, interaction by contact, the example of the book and the table. Here we need a contact point between them. For that we call it interaction by contact. Where the example between the book and Earth, no need for a contact point. The interaction acts from a distance. So Newton's third law, or principle of interaction, for every action there is an equal and opposite reaction. And F1 on 2 vector equal to minus F2 on 1 vector. And again, the minus sign represents that the two forces have different directions. While They have same magnitude. F1 on 2 equal F2 on 1. Let us check this example about the interaction by contact. This cannon will apply an action on the shell. Simultaneously, the shell will apply a force on the cannon, which is the reaction force. Let us watch this video. The cannon apply a force on the shell. Simultaneously, the shell push the cannon backward in a reaction force. Here we can see interaction acting from a distance. A big stationary magnet, the red and blue, here north and south pole of the magnet. And we have a fan that we fixed on each blade a magnet. At the left side, the blue magnets are attracted by the stationary red magnet, while at the right side, the red magnets are repelled by the stationary red magnet. For that, we are getting a continuous rotational fan. Why this happening? Since opposite poles attract each other, while like poles repel each other. The north-north repel each other, and the south-south repel each other. Here are another two examples about interaction by contact, while launching a rocket or while launching a balloon. Let us see this animation. So let us launch the rocket and the balloon. Okay, we can see here that the rocket is applying an action on the air below it. At the same instant, the air is applying a reaction on the rocket vertically upward. So the red arrow is the action of the rocket on the air. So this force is applying on the air. While the blue arrow is the force applying by the air on the rocket. So this blue arrow is on the rocket. Here we can remember that the action and reaction will never act on the same body. They are acting on different bodies, the rocket and the air. Same to the balloon. Here the balloon is applying an action on the air, the red arrow, and at the same instant, the air is applying a reaction on the balloon, which is the blue arrow. And as we notice in the two examples, the action and reaction have always same line of action, same magnitude, but opposite directions. Here a girl rubbing the balloons with her hair. Thus the two balloons have the same sign of charge. Negative, negative, thus they will repel each other. While if she approached the balloon to the wall, the balloon sticks to the wall, because plus and minus, they will attract each other. Unlike charges attract each other, while like charges repel each other. Minus minus will repel, and plus plus they will repel each other. Of course, keep in your mind that the relation for the action and reaction is F1 on 2 vector equal minus F2 on 1 vector. So the minus sign represents that the directions are opposite. While as magnitude F1 on 2 equal F2 on 1. Let us check this animation. Here if we have two unlike charges, positive charge and negative charge, we can see that they will attract each other by action and reaction forces F2 on 1 and F1 on 2. If I have like charges, negative and negative, they will repel each other by equal forces but different directions. Also, if we have two positive charges, they will repel each other by two forces, action and reaction, that have same line of action, equal magnitude, but different directions. Here it's a simple experiment to prove that the magnitudes of the action and reaction are equal. Here we have two spring balances that can measure 10 Newton each. If we pull it from one side, then the spring balance will read 2 Newton. But also the second one read the same magnitude, which is also 2 Newton. If I pull the second one, here the spring balance is reading 5 Newton, but also the second one reads the same number, 5 Newton. This proves that the magnitudes of the action and reaction are equal. Equilibrium of a body. We have this boy standing in his room. We can observe that the boy is at rest. Also his table at rest, and the lamp also at rest. What are the forces acting on the boy? We all know that he has the weight and the normal. The weight vertically downward and the normal vertically upward. Also the lamp has two forces, the weight vertically downward and the tension vertically upward. Even though in the two examples we have forces acting on the objects, although they are at rest, so we say that these objects are in equilibrium. Any body is subjected to two forces, is in equilibrium if the two forces have same line of action, same magnitude, opposite directions. We can notice that the three conditions are the same as the action and reaction conditions, but there is a very important difference between the two. Here the two forces should be on the same body, but as you remember, the action and reaction will never be on the same body. They should be on different bodies. Any object is at rest or in equilibrium, the summation of the forces on this object equal to zero. Here we have only two forces, so F1 plus F2 vector equal to 0 vector. Let us consider a book on a table. What are the forces acting on the book? We all know the weight, which is vertically downward from the center of gravity of the book, the green point. And the second force is the normal reaction, which is vertically upward, and the point of application is the contact point between the book and the table, the green point also. Let us apply the equilibrium condition. Since the book is in equilibrium, then the summation of forces equal to 0 vector. What are the two forces acting on the book now? F1 plus F2 equal to 0 vector. Here the two forces are the normal reaction and the weight. So I can write n vector plus mg vector equal to 0 vector. We can rearrange the equation and we can write n vector equal to minus mg vector. Since we took mg after the equal, the plus will become minus. So n vector equal to minus mg vector. And this is the vector relation for the equilibrium condition. And we can notice that the minus sign represents that n and mg are opposite. The magnitude relation is n equal mg without vectors. And of course we remove the negative sign. So as magnitude they are equal, and as vectors they are equal but opposite. This is another example. A ball is hanging by a rope from the ceiling. What are the forces acting on the ball? Again, the weight vertically downward, the mg. Second, the tension, and the point of application of the tension is the contact point between the rope and the ball. Again, the ball is at rest. Let us apply the condition of equilibrium. Since the ball is in equilibrium, summation of forces equal to 0 vector. F1 plus F2 vector equal to 0 vector. Here the two vectors are the tension and the mg, the weight. So tension vector plus mg vector equal to 0 vector. And again we can rearrange tension vector equal minus mg vector, and this is the vector relation for equilibrium. Here also the magnitudes are equal and tension equal to mg. Now our last part, Hooke's law. We have a spring here of length L0. L0 is the initial length of the spring. When the spring is free, we call it free length or the initial length. Since no mass is suspended from the spring, then we call this spring free spring, and the length of the spring is called the initial length L0. What if we hang a mass from the spring? The spring will elongate, and its length will become L. And L is the length of the spring after hanging the mass. So how much the spring elongated? This elongation we denote it by delta L or x. So this delta L is the elongation of the spring, x or delta L equal to L minus L0, equal to the final length of the spring minus the initial length of the spring L0. We have another free spring. The L0 is the initial length of the spring. If we compress this spring by applying a force on it, then its length will become L. Here L is the length of the spring after applying the force F. Now L0 is greater than L. So the compression of the spring is delta L also, but now it's L0 minus L. So always delta L should be positive if it is compression or elongation. For that we can write elongation or compression of a spring is delta L equal to absolute L minus L0. So we can write it L minus L0 or L0 minus L by absolute, always the bigger minus the smaller. Here I can apply a force to elongate the spring, and the final length is greater than the initial length. Or we can apply a force of compression and the final length is smaller than the initial length L0. Delta L is expressed in meter. So here, what are the forces acting on the mass? We have two forces here, the weight vertically downward from the center of the gravity and the tension vertically upward along the spring. So let us apply the condition of equilibrium since the mass is in equilibrium. Summation of forces equal to 0. Here the two forces are the tension and the weight. So tension vector plus mg vector equal to 0 vector. And again tension vector equal minus mg vector. As magnitude, T equal to mg. So if we have the mass of the object, we can calculate the tension along the string. Let us study how T and delta L varies with respect to each other. So the tension versus the elongation delta L. Here I'll take the delta L in centimeter and the tension in Newton. And I'm using here the scale. For each division, horizontal division is 0.5 centimeter and the vertical division is 0.5 Newton. Let us do the experiment together. Here we have the free spring, nothing suspended from the spring, then we call it free spring, and L0 is the initial length of the spring. We are going to suspend 100 grams to the spring, and by the help of a ruler, I will measure L0. L0 is approximately 5 centimeters. This is the initial length of the spring, L0. Here the final length of the spring after elongation, this is L, and the ruler will indicate approximately 6.5 centimeters. So now we know L0 equal to 5 centimeters and L equal to 6.5 centimeters. The length of the spring is 6.5 centimeters after we suspend the mass 100 grams, which is 0.1 kilogram. Of course, we divide by 1000 or we multiply by 10 to the power minus 3. And as we said, if we know the mass of the body, then we can calculate the tension. Tension equal to the weight, and the weight equal mass times gravity. Mass is 0.1, gravity is 10, and the tension is 1 Newton. Now I can calculate delta L. Delta L is L minus L0. L is 6.5 and L0 is 5. Delta L is 1.5 centimeter. So now we can draw 2 points on the graph. And as we said, we are taking the scale 0.5 centimeter on the horizontal division and 0.5 Newton on the vertical division. So we can write here 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. Each division we are increasing 0.5. Also on the vertical divisions, 0.5, 1, 1.5, 2, 2.5, and 3. Each division we are increasing 0.5. So the first point, when the spring is free, the mass is 0. So the tension is 0. No force is applied on the free spring. The elongation was 0. So the first point I can mark on the graph is 0, 0. The second point we can trace on the graph is 1.5 centimeter corresponding to 1 Newton. So here from 1 Newton, I draw a dotted line, and from 1.5 I draw another dotted line. This is my second point. Now let us change the mass. We will suspend a 250 grams. Here the final length is approximately 9 centimeter. Okay, now we know the initial length 5 centimeter and the final length is 9 centimeters. Of course, L equal 9 centimeter corresponding to the mass of 250 grams, which is 0.25 kilogram. Then we can calculate the tension. Tension equal to the weight, M times G, equals 0.25 times 10 equal to 2.5 newtons. Also, we can calculate delta L. Delta L equal L minus L0, and here 9 minus 5, which is 4 centimeters. Again, we can trace the third point. 4 centimeters corresponds to 2.5 newtons. And here 2.5 newtons, horizontal dotted line, and we get our point. Now we can join the points to get our graph. And this is the first point, second point, and third point, and this one is a straight line passing through the origin. So from this graph, we can show that the variation of the tension as function of the elongation or compression of the spring is a straight line passing through the origin, and it indicates that the force and elongation are directly proportional. So T equal K times delta L, and K is a constant equal to the slope of the straight line. So the slope represents the stiffness or the constant of the spring. Each spring has its own stiffness and own constant. So we reach to Hooke's law. T equal K delta L. T is the tension force expressed in Newton. Delta L is the elongation or compression of the spring expressed in meter. And K is the stiffness or the constant of the spring expressed in Newton per meter. And Hooke's law states the tension in the spring is proportional to the corresponding elongation, T equal K delta L. We can see here different type of springs. The third one has lower stiffness. If we hang 100 grams to the second spring, of course we should wait till the mass be at rest or in equilibrium. If we hang a bigger mass, look what happened. We damaged the spring. This spring is no longer Hookean or no longer elastic since it cannot return to its initial length. This one, if we remove the 100 gram, it will go back to its initial length, where this one, it's unable to go back to its initial length. Let us discuss this idea. This spring is a Hookean spring. It obeys Hooke's law. The tension is proportional to the elongation. When we exceed the maximum force, the spring didn't go back to its initial length and it was damaged. And sometimes if we increase the force more, we can break the spring. If the spring obeys Hooke's law, then the graph should be a straight line passing to the origin, and this region we call it elastic region. While if we exceed the maximum force, the graph will no longer be a straight line, and this green graph is the plastic region. And here in this region, the spring is no longer a Hookean spring. It's unable to go back to its initial length. And if we increase the force more, this is the fracture point where the spring breaks.